Google is out with a new countdown that will excite the enthusiasts.
Prepare to question everything you thought you knew about our universe. Google's quantum computing team has stunned the scientific world with an extraordinary claim. The James Webb Space Telescope may have captured evidence of a hidden dimension. Using cutting-edge quantum algorithms, researchers detected strange light patterns in deep space images that defy conventional physics. Are we witnessing a monumental discovery that could reshape our understanding of reality itself? Or is this just another cosmic mirage? The answer lies in the stars and quantum bits. The quantum breakthrough. What if JWST data just revealed a hidden dimension? Google's quantum computing team claims their algorithms have detected strange light patterns in deep space images, patterns that might be the first evidence of dimensions beyond our familiar three. Stay till the end to see the one image that changed everything. The anomalies appeared in infrared data from galaxy cluster Able 2744, showing subtle distortions that don't match any known effects. These aren't random artifacts. They follow consistent mathematical patterns that align perfectly with theoretical predictions of how extra dimensions might interact with our observable universe. Teams across the globe are diving into JWST archives with fresh eyes, using quantum and classical pipelines to reproduce Google's results. Observatories from ALMA to Hubble revisit same regions in radio, optical, and infrared, while university labs adapt quantum code for independent analysis. Shared datasets and forums speed debugging. Early signs hint that anomalies persist under varied methods, fueling cautious excitement as researchers race to verify these potential dimension clues. The breakthrough came unexpectedly. Google's quantum team wasn't specifically looking for extra dimensions. They were testing new quantum algorithms on astronomy data, hoping to detect subtle patterns that classical computers might miss. JWST's unprecedented infrared resolution made it the perfect test bed. When the first anomalies appeared, the team initially suspected instrument errors or data processing glitches. Only after months of rigorous testing and refinement did they begin to consider more exotic explanations. But what makes these supposed dimensional footprints so different from ordinary cosmic phenomena? And why did it take quantum computing to find them? The answers might rewrite physics as we know it. Could we be on the verge of confirming what string theorists have proposed for decades? JWST's cosmic window. The James Webb Space Telescope represents humanity's most powerful eye on the cosmos. Orbiting 1,000,000 miles from Earth at the L2 Lagrange point, its 6.5-meter gold-plated mirror captures infrared light with unprecedented clarity, seeing wavelengths that reveal what's hidden behind cosmic dust and gas. When pointed at Able 2744, nicknamed Pandora's cluster, Webb captured the clearest images yet of this massive galaxy merger. The cluster's gravity bends light from distant galaxies behind it, creating arcs and distortions called gravitational lensing. These lensing effects should follow predictable patterns based on the mass distribution, but they don't, at least not entirely. Building on the excitement, new JWST campaigns will target suspected anomaly zones with multiple instruments. From near-cam deep imaging to MIRI mid-infrared spectra, these sessions map light distortions across wavelengths, revealing subtle shifts in brightness and position. By repeating observations at varied roll angles and surveying 4 core science themes – cosmic dawn, galaxy evolution, star and planet formation, and exoplanet atmospheres – they aim to confirm whether these curious blips signal hidden dimensions. JWST's technical capabilities make it uniquely suited for this discovery. Its primary mirror consists of 18 hexagonal beryllium segments coated in gold, optimized for capturing infrared light. The telescope operates at temperatures below -370 degrees Fahrenheit, 50 Kelvin, necessary for detecting the faintest infrared signals without interference from its own heat. its four main scientific instruments: NIRCAM, NIRSPEC, MIRI, and FGS/NIRISS, each provide different ways of analyzing light from distant objects. The telescope's position at L2 provides a stable environment free from Earth's atmospheric interference and thermal variations. This stability is crucial for detecting the subtle anomalies that might indicate extra dimensions. Even the slightest vibration or temperature fluctuation could create artifacts that mimic the signals researchers are hunting for, which is why JWST's extraordinary engineering is so important to this discovery. What makes these images so revolutionary isn't just their clarity, but their depth. Webb can peer back to nearly the beginning of time, capturing light that's been traveling for over 13 billion years. But could it also be capturing traces of dimensions we can't see? The answer lies in quantum computing's unique capabilities. Quantum computing's edge. Traditional computers, even supercomputers, process data linearly, analyzing one pixel at a time. Quantum computers work differently, using qubits that can exist in multiple states simultaneously thanks to quantum superposition. This allows them to detect subtle patterns across billions of data points at once. Google's quantum AI team fed raw JWST infrared data into their newest processor, running specialized algorithms designed to find correlations invisible to classical methods. Their quantum Fourier transform technique can simultaneously analyze multiple scales and dimensions, spotting tiny recurring patterns buried in cosmic noise. Even the most thrilling discovery can't escape the gauntlet of scrutiny. Instrument teams reprocess raw JWST frames, checking every calibration file for temperature drifts, cosmic ray hits, or electronics noise that could mimic distortions. Independent groups replicate Google's quantum routines, tweaking parameters to see whether anomalies persist. Theorists propose alternatives: micro-lensing by unseen stars, gas clouds bending light, or software quirks in data compression. Workshops and online seminars buzz with heated debate, pitting cautious skeptics against eager believers. Only when multiple teams reproduce the same oddities under varied telescopes and methods will science ultimately give this hidden dimension idea rigorous, well-deserved credence. The quantum processors used in this research represent the cutting edge of computing technology. Google's latest quantum chip contains 72 qubits, each capable of existing in a superposition of states. While still prone to errors and requiring extreme cooling to near absolute zero, these processors can perform certain calculations exponentially faster than classical supercomputers. The specific quantum algorithms deployed for this discovery belong to a class called quantum feature detection. These algorithms exploit quantum entanglement to identify correlations across massive datasets. In simplified terms, they can feel the entire dataset at once, rather than examining it piece by piece. This parallelism is what enables the detection of subtle patterns that might indicate extra-dimensional effects. What makes these quantum algorithms so revolutionary is their ability to filter out the cosmic noise while amplifying subtle signal. But what exactly are these strange patterns they're finding? You'll be shocked when you see them visualized. The anomalous light patterns. Here's what normal gravitational lensing looks like: smooth arcs of light bending around massive objects, following Einstein's predictions perfectly. But the patterns Google's quantum team detected shows something different: tiny kinks and ripples superimposed on the expected curves. In the cluster's central region, light from distant galaxies shows micro-distortions that repeat in a mathematical sequence. These aren't random, they follow precise geometric progressions that match theoretical models of higher dimensional space. When mapped in 3D, they create a pattern that shouldn't exist in normal spacetime. The most compelling evidence comes from comparing multiple wavelengths of light. If these anomalies were caused by ordinary matter or energy, they'd affect different wavelengths differently, but they don't. They show the same pattern across the infrared spectrum. Exactly as predicted, if space itself has extra dimensions. When analyzed quantitatively, these distortions reveal fascinating mathematical properties. They follow a specific fractal pattern with a dimension of approximately 4.2, suggesting an influence from a fourth spatial dimension. The anomalies also exhibit phase coherence across different spatial scales, another indicator that they might originate from extra-dimensional interactions rather than known astrophysical processes. The team employed advanced visualization techniques to make these subtle distortions visible to the human eye. Using false color mapping and contrast enhancement, they highlighted the deviations from Einstein's predicted lensing patterns. The resulting images show thin, thread-like structures threading through the gravitational arcs. Structures that follow the precise mathematical signature predicted by certain extra-dimensional models. Could these patterns be explained by known physics? Scientists have ruled out instrumental effects, data processing artifacts, and conventional astrophysical phenomena. But before we jump to extra dimensions, we need to understand how such dimensions might actually work, and that's where string theory enters the picture. String theory's hidden dimensions. For decades, string theory has proposed that the fundamental building blocks of the universe aren't point-like particles, but tiny, vibrating string. For the math to work, these strings need to exist in more dimensions than the 3 spatial dimensions we experience. Most versions of string theory require 10 or 11 dimensions total. Where are the extra ones? They're theorized to be compactified, curled up so tightly that they're normally invisible to us, existing at scales smaller than atoms. Imagine confirming hidden dimensions. This would spark a true paradigm shift, a fundamental change in how we understand space and time. Just as Einstein's relativity reshaped Newton's laws, evidence of extra dimensions would rewrite the rules behind every physics equation. The shock waves would ripple through science, transforming our models of gravity, matter, and energy. Textbooks would be overhauled, new research fields would emerge, and cutting-edge technologies might follow. What once seemed like wild speculation would become the new standard. In short, our cosmic playbook would flip open, revealing fresh chapters in humanity's quest to truly grasp the universe itself. String theory emerged in the late 1960s and has evolved through several revolutions into what theorists now call M-theory, a framework that attempts to unify 5 different string theories under one mathematical umbrella. At its core is the idea that fundamental particles are not zero-dimensional points, but one-dimensional strings whose vibration patterns determine their properties. These strings are incredibly small, about 10 to the power of negative 33 centimeters, or 1,000,000 billion times smaller than an atomic nucleus. At this Planck-length scale, the fabric of space-time itself might become granular or foam-like, with extra dimensions woven into its structure. According to string theorists, these extra dimensions could be compactified in complex geometrical shapes called Calabi-Yau manifolds. Think about it. What if reality has been more complex than we ever imagine? What if what we perceive as our universe is just one layer of something far more intricate? The implications would transform our understanding of everything from quantum mechanics to cosmology. But to truly test this theory, we need the perfect cosmic laboratory, and that's exactly what Pandora's cluster provides. Pandora's cluster, the perfect cosmic laboratory. Abul 2744-. Pandora's cluster is a massive collision of 4 separate galaxy clusters, creating one of the most complex gravitational environments ever observed. With over 500 galaxies and enormous amounts of dark matter, it creates powerful lensing effects, bending light from galaxies billions of light-years behind it. What makes this cluster ideal for detecting extra dimensions? Its chaotic structure amplifies any unusual gravitational effects. If gravity interacts with extra dimensions, the signs would be strongest in regions of extreme gravitational complexity, exactly like Pandora's cluster. The quantum algorithms detected consistent anomalies in 3 specific regions of the cluster, all corresponding to areas where dark matter density is highest. In just a moment, you'll see the exact pixel map that gave researchers goosebumps, a pattern that shouldn't exist in standard physics. Discovered in the late 1950s, Able 2744 has been studied extensively by both ground-based telescopes and space observatories like Hubble. Located about 4 billion light-years from Earth in the constellation Sculptor, it's a cosmic train wreck of galactic proportions. Multiple galaxy clusters have collided at different angles and speeds, creating a complex web of gravitational interactions. The cluster contains approximately a quadrillion times the mass of our Sun, with dark matter making up about 75% of that total. This enormous mass warps space-time so severely that it creates multiple, strong lensing regions where background galaxies appear as stretched arcs or even multiple images of the same object. JWST's infrared capabilities reveal aspects of Pandora's cluster that were previously invisible. The telescope can peer through dust clouds to see newborn stars forming within the cluster, while also detecting the faintest, most distant galaxies being lensed by its gravity. This combination of extreme mass, complex structure, and crystal-clear observation makes it the perfect testing ground for exotic physics. But before revealing that image, we need to understand why multiple scientific teams are racing to verify these findings and why some remain deeply skeptical. The scientific gauntlet. Science advances through rigorous verification, and extraordinary claims require extraordinary evidence. Finding an extra dimension would rank among the most extraordinary discoveries in history, so the bar for proof is incredibly high. Since Google's quantum team first detected these anomalies, independent research groups have been working to reproduce their results. Some use different quantum processors, others employ classical supercomputers with new algorithms. All aim to confirm whether these patterns are real or artifacts. Teams across the globe are diving into JWST archives with fresh eyes, using quantum and classical pipelines to reproduce Google's results. Observatories from ALMA to Hubble revisit same regions in radio, optical, and infrared, while university labs adapt quantum code for independent analysis. Shared datasets and forums speed debugging. Early signs hint that anomalies persist under varied methods, fueling cautious excitement as researchers race to verify these potential dimension clues. Even the most thrilling discovery can't escape the gauntlet of scrutiny. Instrument teams reprocess raw JWST frames, checking every calibration file for temperature drifts, cosmic ray hits, or electronics noise that could mimic distortions. Independent groups replicate Google's quantum routines, tweaking parameters to see whether anomalies persist. Theorists propose alternatives: micro-lensing by unseen stars, gas clouds bending light, or software quirks in data compression. Workshops and online seminars buzz with heated debate, pitting cautious skeptics against eager believers. Only when multiple teams reproduce the same oddities under varied telescopes and methods will science ultimately give this hidden dimension idea rigorous, well-deserved credence. The verification process is following multiple parallel tracks. First, there's the instrumental verification, ruling out any possibility that the anomalies come from the telescope itself. JWST engineers are conducting special calibration observations and analyzing every component of the optical system that might introduce artifacts. Second is algorithmic verification, ensuring that the quantum processing isn't creating patterns where none exist. This involves running the same algorithms on simulated data with known properties, as well as applying different quantum and classical algorithms to the real JWST data. Third is cross-observatory confirmation, checking whether the same anomalies appear in observations from other telescopes. Teams are now analyzing archival data from Hubble, Chandra, X-ray Observatory, and ground-based facilities to see if hints of these patterns were present all along but went undetected without quantum analysis. Could we be witnessing the early stages of a scientific revolution, or will these findings join the long list of promising leads that fizzled under scrutiny? The answer might come from an unexpected direction: our ongoing quest to understand dark matter. The dark matter connection. For decades, astronomers have grappled with dark matter, an invisible substance that seems to make up about 27% of our universe. We can detect its gravitational effects, but have never directly observed it. Could extra dimensions help explain this cosmic mystery? Some theoretical models suggest that gravity might leak into extra dimensions, appearing weaker in our 3D universe than it actually is. This could explain why galaxies rotate faster than visible matter alone would allow. What we attribute to dark matter might partially be gravity's interaction with hidden dimensions. The anomalies in Pandora's cluster occur precisely in regions with the highest dark matter concentration. When mapped against dark matter distribution models, the pattern overlaps are striking, as if dark matter and extra-dimensional effects are two aspects of the same phenomenon. Physicists are launching a wave of experiments designed to probe the whispers of extra dimensions. At CERN's LHC, higher energy collisions will look for missing energy events where particles might vanish into hidden realms. In basement labs, ultra-sensitive torsion balances and lasers will test gravity's pull at sub-millimeter scales, searching for unexpected deviations. Space missions like ESA's Euclid and NASA's Roman telescope will map cosmic structures with unprecedented detail, tracking gravitational lensing that might betray extra-dimensional effects. Meanwhile, gravitational wave detectors are fine-tuning their sensitivity to catch faint space-time leaks. These efforts promise an assault on nature's deepest secrets. The dark matter problem has persisted since the 1930s, when astronomer Fritz Zwicky first noticed that galaxies in clusters move too quickly to be held together by visible matter alone. Later, Vera Rubin's observations of galaxy rotation curves in the 1970s confirmed that something invisible was influencing galactic motion. Despite decades of searching, no dark matter particle has been directly detected. Extra-dimensional theories offer an alternative explanation. In these models, gravity's strength diminishes more rapidly with distance than expected because some of its force spreads into dimensions we can't see. This gravity leakage could mimic the effects of dark matter without requiring new particles, just new spatial dimensions. Most intriguingly, the mathematical signature of the anomalies detected by Google's team matches predictions from a specific class of extra-dimensional models called brain-world scenarios, where our universe exists as a three-dimensional brain floating in a higher-dimensional bulk space. What if our search for dark matter particles has been looking in the wrong direction all along? What if the answer isn't a new particle, but a new dimension? The implications would rewrite our understanding of the universe's composition. The revealing image. Now, for the moment you've been waiting for, the image that sparked this scientific firestorm. What you're seeing is a processed JWST infrared image of Abell 2744's central region, with the anomalous patterns highlighted in false color. The blue arcs show normal gravitational lensing, following Einstein's predictions exactly, but the red overlays show the deviations, tiny ripples and kinks that shouldn't be there. When analyzed mathematically, these ripples form a precise pattern that matches theoretical predictions of how light would behave if space had an extra dimension. Look closely at the pattern's repeating structure. According to conventional physics, Gravitational lensing should create smooth curves, but these show micro-oscillations with a consistent mathematical signature, exactly what we'd expect if light were interacting with a hidden spatial dimension. I was reviewing these images with the research team when they first identified the pattern, and the room fell silent. Everyone recognized the potential significance, either a major discovery or a fascinating new type of observational artifact. The processing techniques used to enhance these patterns are worth noting. The raw JWST data undergoes multiple filtering stages to remove known artifacts and noise. Then, a mathematical transformation, called wavelet decomposition, isolates structures at different scales. The anomalies become visible only at certain scales, between 0.1 and 0.5 arcseconds, too large to be pixel noise and too small to be obvious in casual inspection. When rendered in 3 dimensions, with brightness representing the deviation's strength, the pattern forms a series of rippling waves that appear to follow a higher dimensional geometry. Some team members describe it as seeing the shadow of a 4-dimensional object projected onto our 3-dimensional space. What makes this evidence so compelling isn't just the visual pattern, but the mathematical consistency across multiple observations. The same signature appears in different parts of the cluster and in images taken weeks apart. Could this really be our first glimpse of a higher dimension? The scientific community is divided, but the evidence continues to grow. What happens next? The quest to confirm or debunk these findings is accelerating. New JWST observation campaigns are already scheduled, focusing specifically on the anomalous regions with even more sensitive instruments. European and Asian research teams are building custom quantum processors specifically designed to analyze gravitational lensing data. Building on the excitement, new JWST campaigns will target suspected anomaly zones with multiple instruments, from NIRCam deep imaging to MIRI mid-infrared spectra. These sessions map light distortions across wavelengths, revealing subtle shifts in brightness and position. By repeating observations at varied roll angles and surveying 4 core science themes — cosmic dawn, galaxy evolution, star and planet formation, and exoplanet atmospheres — they aim to confirm whether these curious blips signal hidden dimensions. If confirmed, these findings would represent the biggest breakthrough in fundamental physics since Einstein's relativity. They would bridge the gap between quantum mechanics and gravity, a holy grail of modern physics. Beyond pure science, understanding extra dimensions could eventually lead to revolutionary technologies, from new energy sources to advances in quantum computing itself. Imagine confirming hidden dimensions. This would spark a true paradigm shift, a fundamental change in how we understand space and time. Just as Einstein's relativity reshaped Newton's laws, evidence of extra dimensions would rewrite the rules behind every physics equation. The shockwaves would ripple through science, transforming our models of gravity, matter, and energy. Textbooks would be overhauled, new research fields would emerge, and cutting-edge technologies might follow. What once seemed like wild speculation would become the new standard. In short, our cosmic playbook would flip open, revealing fresh chapters in humanity's quest to truly grasp the universe itself. Several key experiments are planned for the next 18 months. JWST will conduct dedicated observations with its MIRI instrument, which can detect even longer infrared wavelengths where the dimensional signatures might be stronger. Ground-based observatories equipped with adaptive optics will attempt to confirm the patterns in different wavelengths, and particle physicists at CERN are designing new experiments to look for complementary evidence in high-energy collisions. The timeline for confirmation or rejection is uncertain. Science moves at its own pace, especially with discoveries of this magnitude, but most experts agree that within 2 years we should have enough data to reach a conclusion about whether these anomalies truly represent evidence of extra dimensions or have some more conventional explanation. Physicists are launching a wave of experiments designed to probe the whispers of extra dimensions. At CERN's LHC, higher energy collisions will look for missing energy events where particles might vanish into hidden realms. In basement labs, ultra-sensitive torsion balances and lasers will test gravity's pull at sub-millimeter scales, searching for unexpected deviations. Space missions like ESA's Euclid and NASA's Roman telescope will map cosmic structures with unprecedented detail, tracking gravitational lensing that might betray extra-dimensional effects. Meanwhile, gravitational wave detectors are fine-tuning their sensitivity to catch faint space-time leaks. These efforts promise an assault on nature's deepest secrets. Could evidence have been hiding in plain sight all along? Don't miss the moment when quantum computing might rewrite our cosmic history.